Assalamualaikum warahmatullahi wabarakatuh. Hello guys, this is me Farhan Ramadan Afarabi, and today's subject is Big Bang. What is Big Bang? Do you know what Big Bang is? Okay, let's examine the scientific way. Big Bang. The Big Bang is scientific theory that explains the origin of our universe. In a simple terms, a very long time ago, all the matter and energy in the universe was compressed into an extremely tiny, hard, and dense point called a singularity. Scientists often called it as a dot. This singularity then began to rapidly expand and cool, leading to the formation of everything we know today, such as galaxies, stars, planets, and even us as a human being. Imagine it like a giant explosion, but not an explosion that happened in some specific place. Instead, it was the explosion of space itself. As the universe expanded, it has also cooled down, allowing particles to come together and form various pieces of the evidence. It formed atoms, later on stars and galaxies. The Big Bang theory is supported by various pieces of evidence, such as the observed expansion of the universe and the presence of cosmic microwave background radiation, which is like a faint glow left over from the early moments of the universe. Okay, after the examine of what is Big Bang, I hope you understand what is it. And then let's move on into the next step, how it happened. Okay. This one. How it happened. It happened in nine steps. The first step is T equal zero singularity. The term T zero singularity refers to the idea that at the very beginning of the universe, at time equal zero, there was singularity, a point of infinity, then set of temperature. This concept often associated with the Big Bang theory, lasting from 0 approximately to 10 to the minus 40, 43 seconds after the Big Bang. Okay, after this happened, it was microscopic universe. It happened at 10 to the minus 43 seconds. Also, we can call it as Planck epoch. This one. The Planck epoch refers to the earliest known period of time in the universe, lasting from 0 approximately to the 10 to the minus 43 seconds after the Big Bang. And during this time, the universe was in a state of extreme density and temperature, with the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces united into a single force. The Planck epoch represents an extremely and early microscopic phase of the universe. And this time, the Planck scale is associated with the Planck length, Planck time, Planck energy, which are fundamental units derived from fundamental constants such as speed of light, Planck's constant, and gravitational constant. Okay. Then it's this one. Grand unification epoch happened at 10 to the minus 36 seconds. As the universe expanded and cooled, this force underwent a process called symmetry breaking, leading to the distinct force we observe today. The Grand Unification Epoch is part of the broader understanding of the early moments of the universe, and it's crucial aspect of many models in theoretical physics that aim to describe the fundamental forces and particles in the universe. The idea of symmetry breaking during this epoch is crucial. Symmetry breaking refers to the transition from a more symmetrical state to a less symmetrical one in the early universe as expanded and cooled. The forces that were initially unified started to differentiate into the distinct forces we observe today, such as gravity, electromagnetism, and strong and weak nuclear forces. Then, what happened after this time? Electroweak epoch. The electroweak epoch is another important phase in the early universe, occurring at approximately 10 to the minus 12 seconds after the Big Bang. During this epoch, the electromagnetic force and the weak nuclear force were unified into a single force known as the electroweak force. The electroweak epoch specifically involves the separation of electromagnetic force from the weak nuclear force. Yes. This separation is associated with Higgs field occurring non-zero vacuum expectation value, which give mass to the V and Z bosons, carriers of the weak force. And this breaking of symmetry and subsequent differentiation of forces and set to the stage for distinct force we observe in the universe today. Okay. After this time, it's yeah the quark epoch. The quark epoch occurred at extremely early stage in the universe, specifically around 10 to the minus 6 seconds after the Big Bang. During this epoch, the universe was incredibly hot and dense, with temperatures on the orders of trillions of degrees Celsius. During this quark epoch, the fundamental particles known as quarks and gluons were not confined with protons, neutrons, and other hadrons as they are today. Instead, they freely moved in a hot, dense soup known as the quark-gluon plasma. As the universe continued to cool and expand, it underwent a process called a quark confinement, leading to the conformation of protons and neutrons. Then it was Hadrian, no, we call it a Hadron epoch, occurred at around t equal 1 second after the Big Bang. During this epoch, the universe had cooled it down enough for quarks and gluons to combine and form hadrons, which include protons and neutrons. The transition from the quark epoch to the hadron epoch was characterized by the process of quark confinement. Yep. Yes. The Hadron epoch is critical period in early universe because it marks the transition from state where quarks and gluons freely interacted to a state where protons and neutrons and other hadrons become the dominance of the forms of matter. During this time, nuclear synthesis began. Then is nu- yes, this step is called a nucleosynthesis. Happens at t equal 3 minutes. The universe entered a phase known as Big Bang nucleosynthesis or BBN. During this relatively short period, which lasted for a few minutes, the conditions in the universe were suitable for formation of the light element through a nuclear reaction. The universe had cooled down enough for protons and neutrons to combine and form nuclei of light elements such as hydrogen, helium, and small traces of deuterium, helium-3, and lithium. The exact Abundances of these elements were influenced by density and temperature of the early universe during this specific time frame. The temperature during the first few minutes of the Big Bang were still extremely high, and nuclear reaction could occur at a significant rate. And the next step is recombination. Happened at 300,000 NXT years after the Big Bang. The universe entered a crucial phase known as recombination. During this period, the universe had cooled down sufficiently for charged particles, specifically protons and electrons, to combine and form neutral hydrogen atoms. Before recombination, the universe was filled with hot, ionized plasma of protons and electrons, which scattered protons of light continuously. The formation of neutral hydrogen allowed photons to travel more freely through space without scattering, leading to a significant event known as a cosmic microwave breakdown, or CMB decoupling. The photons that were previously trapped in hot, ionized plasma could now move freely through space. And the temperature at this time was around 300 degrees Celsius, and the universe continued to expand and cool. And the last time it's T equal 150 million years, and we can call it as formation of galaxies and stars. Around 150 million years after the Big Bang until now, the universe went through big changes. First, gravity created large structures like galaxies. Then the first generation of stars, often referred to as population of the third stars, is believed to have formed around 100 and 300 million of years after the Big Bang, made mostly of hydrogen and so on. And this is the picture. Can you see the picture right? From the here is the Big Bang until the here, a lot of that. Like I said before, gravity created a large structure like galaxy. Can you see that? That was galaxies. In front of the galaxy is the planets, and it happened in 100 to 3 million years after the Big Bang. And all of that was created by hydrogen and helium. These stars gave off light that changed the universe from mostly dark to bright. And until now, galaxies continue to evolve through mergers, interaction, and gas accretion, resulting in diverse shapes and population of stars over billions of years. Within these galaxies, stars form planetary systems, including our own solar system, Milky Way. Our sun is part of galaxy, and in some of these galaxies, planet Earth form. And as time went on, the universe structure evolved, creating cosmic neighborhoods like galaxy clusters. About 5 billion years ago, the universe started expanding faster because of something what we called a dark energy. Okay, I think that's all sequence of the universe itself, and let's end this by things Alhamdulillah. Sorry, I forgot to show you this one. Hmm. I said so before. This was formation of the universe, and this one is recombination, and this one is formation of galaxies. And thank you. I hope you understand what I say. Assalamualaikum warahmatullahi wabarakatuh. Enjoy. And if you still not understand this, please repeat this video and hope you understand enough. Assalamualaikum warahmatullahi wabarakatuh.